Alrighty, so we're gonna jump right into it. So this is the first of two review videos going over the content for Gen Chem 1127. Right, and so just to start out, I wanted to kind of recap the email that I sent earlier today. And so this is kind of the schedule leading up to your final exam, which is on Wednesday, December 16th, and I believe at 8 a.m. Right, so tonight is Monday the 7th. We're going to do a review right now of chapters 1 through 6, right? It's going to be strictly content. There's a couple of questions mixed in there, a couple examples, but not too many. And then tomorrow, we're going to go through the last couple chapters, and I know in SI we never got to chapter 10, and so we'll do a more in-depth look into chapter 10 tomorrow night, right? Then because these are pre-recorded and you guys aren't here and can't ask your questions on the material, I'm going to hold an SI session on Wednesday night, right? It's going to be Q&A, so please bring questions. We're going to do that the normal time, so it's going to be at 7 o'clock p.m. And to access that, you can use the normal link that is on the SI information tab on your Chem page, right? Then in addition to just a content review, right, I'm going to try to release some questions this weekend, some practice questions. So I hope to get those out Saturday, but I might release them Sunday morning, right? And then later on Sunday, I'll post a video of me going through all of those questions. Okay, so the actual questions themselves will be uploaded earlier than the actual video of me going through all the solutions to them. And then the next day, Monday night, we will host another SI session, again at 7 o'clock p.m. with the normal link, where we go over any remaining questions, whether that's content questions or if there's particular questions that you still have in relation to those practice questions that I release. Okay, and so that's the schedule. For many of you, this might be your first finals week, so I'm sure it's quite an adjustment. It's kind of a big deal, and at college, you know, all these exams kind of at once. And so if you don't really know how to prepare, the biggest piece of advice that I would say is it's never too early to start studying. So I know at this point you have about a week and a half until your final exam, but there is definitely no harm, and I highly suggest kind of going through a little bit each day, right? It's kind of hard sometimes to sit down 5-6 hours and just study chemistry over and over and over. I know when I do that, you know, my brain starts to shut off. You start to make little errors. You know, try to space it out. Spend an hour or two each day. You know, maybe today's goal is to go through chapter 1. Tomorrow, you want to go through chapter 2. You know, try to space it out because you will benefit from that. And that is for all your classes as well, right? Just because you have a biology exam tomorrow, you know, sometimes step away from bio, look at a different subject for a bit, and then go back. You know, sometimes taking a short break is really beneficial in your studying. Okay, but in relation to chemistry, right, rewatch some lecture videos, especially the topics and sections you feel weakest on, right? Kind of hand select. You don't have to rewatch every lecture, but definitely pick the ones that are you're most struggling with, right? Exam questions, if you can view your work and past exam questions, I highly recommend reviewing those, going through your work, seeing what errors were made, how to prevent them in the future, that type of thing. Any type of problems, whether they came from discussion, homework, me, or from your lecture, those are all great problems to review. And work on your study review sheets. You know, this is an open note exam. It has to be printed, but just like every other multiple choice in the past, you are allowed to have handwritten notes or things you've printed off online from offline, right? So I would definitely recommend having your periodic table printed off, your equation sheet, maybe your list of polyatomics, especially if you feel kind of weaker on that. And then I would say make some organized notes, you know, but don't put everything in it, right? If you know how to calculate molar mass, don't put that on the sheet, but put the 1 or 2 or 3 or 4 topics from each chapter that you're struggling the most with. Okay, and so just the biggest recommendation I have about sheets for review notes during the exam is just make sure you can find the information quickly, right? You have an hour and a half for 50 multiple choice questions. They write the tests in a way that makes it very manageable to get through them all. But if you have 20 pages of notes and you don't know where to find something, if you need, notes to reference, that might waste 5-10 minutes right there sorting through your notes. So have a quick way to find things in your note packets if you make one. Right? Attend office hours if your TAs and professors still hosting those. Make flashcards. Hopefully you've found some study strategies that have worked for you in this class. Okay, so jumping right into it, right? So each chapter I'm going to kind of outline the main points that I'm going to go over, and just kind of note one thing. Again, this exam I believe is about 50 questions long, and it covers 10 chapters. So realize that on average, they can only write 5 questions per chapter. Okay, so on the final exam, your questions are for the most part on the very big topics within the chapter, right? They don't really aim for those super small details and try to make you remember every little thing in the chapter, right? It's the big categories that you're going to be tested on. So focus first on those and then work your way in and kind of at the end get those little details. But definitely start your studying with the big topics from each chapter. Right, so for chapter 1, we're going to start with classification of matter. Right, so we classify matter into 2 broad categories. We call them pure substances and mixtures. So pure substances have a fixed composition, right? And that's the really important point, fixed composition. So we have elements, which we find on the periodic table, right? Anything on the periodic table is an element. And then we have compounds. So compounds are just going to be made of 2 or more elements. And they are, again, in a fixed or constant composition. Okay, so for example, CO2, carbon dioxide, has the constant composition of 1 carbon to 2 oxygens, right? It will always be in that ratio, and if it's not, then it's not going to be carbon dioxide. It's going to be some other compound. Okay, and the only way we can change these compounds is if they undergo some chemical processes. Okay, now mixtures, on the other hand, can be they have no fixed composition, so that's the big difference. Pure substances has a fixed composition, mixtures do not, and mixtures can also be physically separated. Okay, and we have 2 different types of mixtures. We have heterogeneous mixtures, which vary from point to point, and so the classic example of this is a pepperoni pizza. Right, on one slice you might have a lot of pepperoni, a lot of cheese, but not a lot of sauce. While on another piece, it might be loaded with sauce and you might have only 1 piece of pepperoni and just a little bit of cheese, right? Every single piece, every single spot is a little bit different. Now we also have homogeneous mixtures, which are known as solutions. Okay, and solutions are uniform in composition. So an example of this would be like if you dissolved sodium chloride into water, right, to make salt water. Now, by a homogeneous mixture being uniform in composition, that means that if you had a beaker of salt water, right, and you were to look at 1 drop of water, and if you could actually see the atoms in that water or in that droplet, right, that means that in every drop you might have 9 molecules of water and 1 molecule of NaCl in every single spot that you test, right? Every single spot should be approximately the same. Okay, but definitely note the difference between uniform composition and no fixed composition. Okay, a solution having a uniform composition, again, means that every single drop of that saltwater solution you made will theoretically have the same amount of water molecules and the same amount of NaCl. Okay, but the fact that it has no fixed composition means that if you have 2 different solutions of salt water, right, NaCl water, then those might not be identical, right? One, if you take a drop of water from one of the solutions, it might have 100 molecules of water and 1 molecule of NaCl, while the other solution might have 500 molecules of water and only 1 molecule of NaCl in that drop, right? So within a single solution, it's uniform, but homogeneous mixtures can vary from one to another, right? Two different saltwater solutions are going to be different from one another, while when we look at compounds above, one molecule of carbon dioxide is always going to be exactly the same as another molecule of carbon dioxide. Okay, properties of matter, right? So we have chemical and physical properties. So chemicals going to deal with the identity of the matter. And so definitely note these kind of keywords under the examples. If you ever see the terms flammability, acidity, reactivity, burning, or combustion, that should automatically set alarms off in your head saying that we're dealing with some sort of chemical characteristic and property, right? On the other end, we also have physical properties, which are our observable characteristics, right? And so the big ones to note for this, I'm sure you guys know that physical property would be the mass, the volume, the color, the density. But the big ones that sometimes people forget about is that the state change is a physical property and that conductivity is a physical property, right? If we have a copper wire and we send electricity through it, right, it's conducting electrons, but the copper wire is still copper, right? It's not actually changing the chemical identity, and so conductivity is a physical property, right? Same for state change. If we boil water and it becomes water vapor, right, it's still H2O. It's still the same chemical. It's just in the gas phase, not the liquid, okay? And so state change is, again, a physical property. And then this is something that I don't know if they would ask. It's kind of a small point, so maybe this is something you just write on your sheet, just worst case, in case they ask it, you know it. But there are also extensive and intensive properties. So intensive, starting with an I, is independent of quantity, right? So it doesn't matter if you have a truckload or I don't know, 1 gram of silver, right? The density of that silver would still be identical, right? It doesn't matter how much of it you have. Intensive properties like density would not change. Another example of an intensive property would be like color, right? It doesn't matter if you have a couple grains of sand or you are on a beach of sand, it's pretty much all the same color. Assuming you don't have a weird colored sand, but an extensive property, those are dependent on quantity, right? Volume, right? 1 cup of water is very different volume-wise than a quart of water or a gallon. Right, so in this chapter, we also kind of have significant figures. So in order to even do math with them, we first need to know how to count them. So remember that anything that isn't a 0, so all non-zero integers, will always be significant no matter what. Okay, we also have exact numbers, also known as counting numbers, which we consider to have infinite sig figs. So for example, if you say, I have 3 eggs, right? You can't have 3.01 eggs, right? If you have 3 eggs in your hand, that's how many you have. It's an exact number. And so in terms of sig figs, we kind of consider it infinite and we kind of ignore it, right? This is same with conversion factors. So 100 centimeter per 1 meter, we pretend that's kind of infinite sig figs because we say that that is just a true conversion, okay? But zeros is where sig figs get a little more complicated, right? So we have 3 types of zeros. We have leading zeros, which come before our non-zero integers, which are never significant figures. Doesn't matter if there's a decimal point or not, they're just never significant. Okay, captive zeros, which come between non-zero integers, will always be significant, right? So it's like that 0 in between the 2 and the 7. And then trailing zeros are zeros that come after our non-zero integers. And these will be significant if there is a decimal point present, right? So see in this middle here, 0.0220. So this last 0 after the 2's is significant and is a trailing 0. And it's significant because it's behind this decimal point, okay? Now, how do we apply this to math or any calculations, right? So when we're doing addition and subtraction, when we do that mathematical operation, our answer has to have the same number of decimal places as the term with the least amount, right? So if we add 1.1, let's say we add 1.15 to 2, right? So 1.15 plus 2. So when you do that math, it would come out to 3.15. But in terms of sig figs, we have to round that to the number of decimal places as the term with the least many. So 1.15 had 2 decimal places, but the number 2, assuming it wasn't exact, that they just said 2 and didn't say it was exact, that has 0 decimal places, which means our answer would actually be rounded to 3, because 3, the answer, should have 0 decimal places. Okay, and then in multiplication and division, right, your answer is going to have to be the same number of sig figs as the term or component with the fewest number. Okay, so addition and subtraction, remember, it's completely based on decimal places. Multiplication and division is going to be based on number of sig figs directly. And then here's your rule for logarithm, right? Your answer should have the same number of decimal places as the number of sig figs in the logarithm, right? So when you take the logarithm of x, right, your answer should have same number of decimal places as significant figures in that value of x. That's maybe, again, something that I'd write down on my sheet in case you see it, but that's not really something that comes up often in this class. Okay, and so an example of some calculations with sig figs. So if we have 13.2 minus 12.48 over 0.55, what should our answer be to the correct number of sig figs? So you're going to start with the math in the numerator, right? So we're going to do the subtraction, and when we do it, it comes out to 0.72. Okay, now I never round, or I try not to round my answers until the end of the problem, because that can just affect the accuracy of your answer, right? So I'm going to keep 0.72 in my numerator for my calculation, but how many sig figs should it be? So when I look over at my two terms involved in the subtraction, 13.2 only has 1 decimal point, while the other number, 12.48, has 2. So because of this, the answer to this subtraction should actually only be 1 decimal point. It should only be 1 decimal point because of my sig fig rules. And so what I do is I actually draw an arrow telling me that this number should end at the 7, right? That 7 should actually be my only significant figure, but I'm going to leave the 2 just so my answer is slightly more accurate, right? And so when I do this division, 0.72 divided by 0.55, and I employ my division rules for sig figs, right, my numerator should really be at the 7, which is 1 sig fig, and my denominator is 2 sig figs, meaning my overall end answer should only be 1 significant figure, again, because of the numerator. Okay, another part of this chapter is just our temperature conversions, right? So we mostly in this class use Kelvin. We do sometimes use Celsius, but they could give you any 3 units, right? Fahrenheit, Celsius, or Kelvin, and ask you to convert to any of the other ones, right? And so these 2 equations up here, the top, are actually on your equation sheet, so they are given to you. You just, from the second equation, should be able to derive how to find your temperature in Celsius from Fahrenheit, right? So I kind of just manipulated this equation around. And if you do not feel comfortable doing that, or are unsure how to do that, maybe just write this equation down, because again, this equation at the bottom here is not on your equation sheet. Okay, and just some little notes that, again, they're not major topics in this chapter, but they do come up. So, oops, sorry for putting accuracy in there twice. So accuracy is a measurement, or they're measurements that yield results near the true or accepted value, right? So accuracy is how close are you to what you want, okay? And this is indicated pretty well by this top target, right? It's not the most accurate, but it's a relatively accurate target in shooting, right? So you have these red dots that are kind of like, we can call those our arrows, and our desired or true value would be the bullseye, right? When you're shooting arrows, that's the goal. And so if we look at our shots, right, for the most part, we were kind of around the bullseye. And if we were to kind of take an average of these, right, it would have been pretty good. And so we can say that that top target is relatively accurate. Again, it's not the most accurate, but for the most part, we're close to our desired value. Now, precision is actually comparing our measurements or our trials to each other, right? How close are they? And so this bottom target actually shows precision, right? We're not anywhere close to the center of the target, which is where we want to be, but we are precise to one another, right? When we shoot, all of our shots are really close together, okay? And so the bottom target, we would not be accurate, but we would be precise, okay? And then also remember in this chapter, we cover an introduction to density. So density is just our mass divided by our volume. And our units for this are more likely than not grams per milliliter. And just remember that a milliliter and a centimeter cubed are the same exact thing. Why do we have density? We have density to allow ourselves to be able to convert from volume to mass or vice versa. And the last point of chapter 1 that I wanted to remind you all of is just dimensional analysis and our conversions. Okay, and I'm sure most dimensional analysis you're very familiar with by now, but I wanted to bring up again when we have squared or cubed units, right? So let's say we have this little patch of fence, right? A classic example of a little fence that's 16 inches by 12 inches. It's a very tiny fence. And so if we were to take the area enclosed in by this fence, right, it would be 192 inches squared. Now let's say they wanted this measurement in terms of meters squared. How would we do this? So we'd convert inches to centimeters, right? So 1 inch is 2.54 centimeters, and then 100 centimeters is 1 meter. But we want all of our units to cancel, right? We have inches squared, and then in the denominator next to it, we have just inches and centimeters above it. And so in order for our inches squared to cancel out, we actually need to square our units, right? So we're going to square, so it's inches squared in the denominator, centimeters squared in the numerator. Then we're going to square our next conversion factors so that we have centimeters squared in the denominator and meters squared in the numerator. And then when our units cancel out, we get meters squared. Right, so just remember when you have units that are squared or cubed, remember that you may, depending on what your units are at the end, need to square and cube your conversion factors as well. Okay, let's jump into chapter 2. So I'm sure by now we're all familiar with the parts of the atom. So the nucleus holds, it's positively charged because it has protons, which have a mass of 1 atomic mass unit and a charge of +1. Neutrons have no charge, or they're neutral in charge, and they also have a mass of 1 AMU, or atomic mass unit, right? So we pretty much assume that the entire mass of an atom is within the nucleus, okay? Because around the nucleus are our electrons in our electron orbitals, right? We assume, or make the pretty basic assumption that electrons have negligible or 0 mass, but we do say that they have a -1 charge, right? So that opposes the +1 charge of the protons. Okay, and when we have atoms, if they have asymmetric charge, right? So if they have more or less electrons than protons, then they'll have a charge and they'll be what we call ions. Okay, and then we also have what we call isotopes, which is a type of atom that has a different number of neutrons, right? So carbon typically has 12 neutrons, but we also have carbon-14, which would have 2 extra neutrons, right? It would have 8 neutrons compared to 6 as to normal. Okay, and we actually use this symbol, the atomic symbol, to denote a particular atom. right? So this is the generic form on the left here, with X being the element symbol. That's what's on the periodic table. A, which is a superscript to the left, is going to be our mass number, which is how many protons and neutrons the element has. Z, the subscript to the left, is our atomic number, which is the number of protons an element has. And then to the upper right, where C is, that's going to be our charge. Okay, and remember that charge, or we only have a charge due to gain or loss of electrons, right? A charge is never created by a change in protons, okay, when looking at a singular atom like this. And so the example to the right, fluorine with a -1 charge and 21. So that's saying our element symbol, or the actual element we're dealing with, is fluorine, right? The number of protons plus neutrons in this fluorine has to be 21. You might notice that Z, or the atomic number, is missing. That's actually a pretty common thing not to have. And the reason for it is that based on your element symbol, you automatically know your atomic number, right? Fluorine, by definition, will always have 9 protons. If it does not have nine protons, it is not fluorine. Okay, so knowing that fluorine has 9 protons, we can pretty quickly figure out that fluorine has 12 neutrons. And if fluorine has 9 protons and has a -1 charge, which means it has 1 more electron than proton, then this fluorine would have 10 electrons. Okay. We also have an introduction in this chapter to the periodic table, right? So we know that it is organized into periods and groups, with the periods being rows of the periodic table, right? You'll kind of know by now that that is kind of organized in a way that makes sense for electron configuration. And the groups, which are the columns of the periodic table, are organized by chemicals with similar patterns of behavior. Right, so group or column 1, known as the alkali metals, they like to get a +1 charge, right? Because if they have a +1 charge, they, in terms of their electrons, will be similar to noble gases, right? Every element wants to be like the noble gases. And so alkali metals are that first group, and you should know all of these groups by name, right? So group 2, you should know, is named alkali earth metals. They like to form a +2 charge, right? Group 3 through 12 is our transition metals. These can vary in charge, which we'll touch on in just a second when we get to naming. Halogens, which is group 17, they like to get -1 charges, right? That's your fluorine, chlorine, bromine, iodine. And then group 18 is our noble gases. We don't really talk about them much in this class because they are very unreactive, right? They don't often participate in chemical reactions. Okay, and so here's the periodic table. So not only, again, the columns are organized by kind of chemical behavior. Okay, the rows, or the periods, kind of have to do with electron configuration. And also remember that for the most part, on the left-hand side of the table, we have our metals. On the right-hand side of the table, we have our non-metals. And this kind of yellow-green portion between the yellow and the lighter green section is our metalloids, right? Which are kind of, they have properties in between metals and non-metals. Okay, and knowing where metals and non-metals are on the periodic table is important for bonding, right? So if we are dealing with a compound with a metal and a non-metal in it, we can pretty much automatically know that they are ionically bound, right? So ionic bonding is between a metal, which is going to have a positive charge, and a non-metal that has a negative charge, right? And in ionic bonding, we see a transfer of an electron from the cation, which is the metal, to the non-metal anion. And then we see an attraction of opposite charges. Well, we also have covalent bonding, right? So covalent bonding is going to occur only between non-metals, right? We won't see metals in covalent bonds. And in covalent bonds, the electrons are going to be shared between the atoms. Okay, and it's important to be able to distinguish ionic from covalent compounds because we have different ways to name them, right? And so if we have ionic compounds, which will again have a positively charged cation and a negatively charged anion, we're going to name it in this way. So our cation, we're going to, if it's in group 1 or 2, just state the name of the atom, right? So down below, one of my examples, actually both my examples, lithium or barium, right? Those are group 1 and 2. We just state the name of the atom. If the cation is a transition metal, we have to take a slightly different approach, right? We have to state the atom's name, but we also need to follow it with the charge in Roman numerals, right? So an example of that would be iron 3 oxide, something like that, right? So you have to specify the charge in Roman numerals. Now the anion, we have 2 different types. We have monatomic anions, which are the 2 examples below, or sorry, the first example below. So monatomic just means it is an anion made of a single atom, right? And whenever you have a monatomic anion, you're just going to write the root of the atom and then add "-ide" to the suffix, right? So Li2S would be lithium, my cation, and then sulfide, right? So sulfur, but we change the suffix to "-ide." Okay, if we have a polyatomic, right, from the sheets that you had to know, all the names of those 4, you just state it, right? You don't change the suffix to "-ide, you just keep the suffix as you know from your polyatomic sheet, right? So barium carbonate, right? We don't change CO3 minus, CO3 2 minus to carbonide, right? It's barium carbonate. Okay, and the big thing to remember about ionic compounds is that your charges balance, right? So sometimes you'll be given a formula and you'll be asked what is the name of the compound. And remember that your negatively charged anion, positively charged cations need to balance in charges, and that you can use that principle to figure out what the charge on your transition metals are, right? So Fe2O3 would be iron 3 oxide, right? Because oxygen, there are 3 of them, each with a -2 charge, a total of -6, and there are 2 irons. So -6 is counteracted by +6. +6 divided by those 2 irons means each iron has a +3 charge. Okay, naming polyatomics. So for the most part, you do need to remember the name of your polyatomics, but these are just 2 tricks that might be able to help you with oxoanions, which are anions with multiple atoms, one of them being oxygen, right? And so we see a couple different examples where we have 2 forms or 4 forms of oxoanions, okay? And the rule of thumb is that the form with the higher number of oxygens ends in -ate, and the form with the lower number of oxygens is -ite. Okay, so we see this in sulfate and sulfite. We also see this in nitrate and nitrite. Now, when there are 4 forms, right, they typically follow this general rule. So it's going to be O4 minus, right? The charge on all of them is going to be -1. We just change how many oxygens we have. And we typically see this with our halogens, right? So we'll see this with chlorine, bromine, and iodine. And if we have 4 oxygens, we're going to use this template, right? 3, we're going to use the template below, 2 and 1 respectively. And I'm sorry, that's supposed to have a Y. I missed that. Hypo blank ite. And so it'd be perchlorate, chlorate, chlorite, and hypochlorite. Again, there should be a Y there. I apologize. Okay. And again, that's just to help you be able to name your polyatomics. Okay, how do we name covalent compounds? So the covalent compounds we are asked to name typically only include 2 atoms, right? The first one, we're going to add a prefix and then just write the atom's name. Now the caveat to this is if the prefix is mono, we don't need to include it, right? So CO2, we don't write mono carbon dioxide, we just write carbon dioxide. Okay. When we look at the second atom, you are always going to add the prefix for the second atom. Then you're going to add the root of that second atom, followed by the suffix "ide," right? So again, carbon dioxide, di meaning 2 oxygens, and the suffix, again, "ide." We also see this with sulfur. Again, the first one, we just write the name, and because there's one of them, we don't write mono, so it's just sulfur, hexa, the prefix for 6, and then fluor, the suffix "ide." Okay, and sorry about that. Here are your prefixes here, if you're not familiar with them, 1 through 10. And then lastly, for naming, the last part of this chapter is naming acids, right? So we have something that's called binary acids. So binary acids have 2 components. One is hydrogen, and the other is just the other component. So I'm denoting that with X. And X is typically a halogen. And if you don't see it as a halogen, the only other atom you'll probably see there is going to be sulfur, right? So it's and the way to name this is you're going to plug the stem of the atom into hydroblankic acid, right? So hydrochloric acid, hydrobromic acid, hydrosulfuric acid, okay? And so whenever you have a binary acid, you're going to plug the stem into hydroblankic acid. If you're doing an acid of your polyatomics, right, we kind of have a rule of thumb that says just change the ending from ate to ick and ite to us, right? So I use the acid of nitrate and nitrite as an example. And so nitrate becomes nitric acid and nitrite becomes nitrous acid. Alrighty, jumping into chapter 3, we focus here on isotopes, coming up with molar mass, balancing chemical equations, and then we jump into stoichiometry and coming up with empirical molecular formulas. Right, so remember we have isotopes, which are forms of atoms with different number of neutrons. And so when we look at a mass on the periodic table, that's actually an average atomic mass, right? And it's a weighted average of all the isotopes of each atom, right? And so we can calculate this average atomic mass by, again, doing a weighted average. And so to do a weighted average, we're going to take the mass of each individual isotope and multiply it by the decimal form of its percent abundance, right? So let's say you have 2 isotopes. Isotope 1 has 60% abundance. The isotope 2 is 40% abundance. Then to find your average atomic mass, you would take the mass of isotope 1 and multiply it by 0.6, right? Decimal form of its percent abundance. And you would add that to the mass of isotope 2 multiplied by 0.4, which is the decimal form of its percent abundance. And so we have 2 basic problems that we most often see, or actually, I would say we have 3, okay? The first example is where they give you all the masses of the isotopes and all the percent abundances, and you just plug it into this equation and you just solve for your average atomic mass. It's just very straightforward, okay? The other 2 common setups is typically what they ask more because they're a little bit harder, right? And so in the other 2 types of questions, you typically have 2 isotopes, okay? And in the first one, you might be given the mass and percent abundance from one isotope, but you might be missing all the information for the other isotope. And so the jump that you need to make here is that your percent abundances always need to add up to 100%, okay? And so knowing the percent abundance of one isotope, you can actually find the percent abundance of the other isotope. And then from there, if you plug in all the numbers into the equation, the only thing you shouldn't know is the mass of a single isotope. And so you would just plug X in for that and you would solve. The other common type of question is where you have 2 types of isotopes and you'll also be given the average atomic mass and you'll be missing both of the percent abundances, right? And so what you have to do for this is you have to assign variables, right? So you might say that the percent abundance of isotope 1 is X, the percent abundance of isotope 2 is Y. And then you have to make the relationship that X plus Y would have to equal 100%. And then you have to do a substitution reaction to find, to solve for just X, for example, and then you have to go back and plug in for Y, right? So you have to do a substitution reaction in this last situation. Okay, a mole. So remember that a mole is 6.022 times 10 to the 23rd of anything, right? That's called Avogadro's number, right? And remember that a mole isn't necessarily just in chemistry, right? You can have a mole of crayons if you have 6.022 times 10 to the 23rd crayons. Okay, and so one way that this comes up is they might say in 1 gram of hydrogen, how many electrons do you have, right? So you'd have to convert 1 gram of hydrogen to 1 mole of hydrogen. Then you could use Avogadro's number as a conversion factor and say 1 mole of hydrogen is 6.022 times 10 to the 23rd atoms of hydrogen. And then in each atom of hydrogen, you have 1 electron, right? That would be kind of your dimensional analysis there. Okay, and then we also have, again, molar mass. I'm sure you guys are all familiar. That's just how heavy or how much mass a single mole of a compound is, right? So that's just the number on the periodic table, right? 1 mole of carbon is 12.01 grams, right? It would be grams per mole would be the units of that. So again, molar mass is just on the periodic table. If it's an element or if it's a compound, you have to add them up, right? So diatomic oxygen, O2, is 2 times the molar mass of just oxygen. So 2 times 16, and so diatomic oxygen is 32 grams per mole. Okay, mass percent of X, right? Any element can be X, would be the mass of that individual element in a compound divided by the total mass of the compound. Okay, and one thing I want to point out is that this is an intrinsic property, right? Meaning it is independent of mass, right? Whether you have 5 grams of carbon dioxide or 100,000 grams of carbon dioxide, the mass percent of carbon in that carbon dioxide is always going to be the exact same. Okay, and to do that calculation, it would be the mass of carbon in CO2, which would be 12.01 grams, divided by the entire mass of CO2, which I believe is 44.01 grams. Okay, balancing equations. So remember, when you're writing an equation, always have to include the states of matter, right? And that we need to make sure that we have equal amounts of every single atom on our reactant and product side. Okay, and what I'm going to say about this mostly is just when you're taking the final exam, just take a couple seconds to make sure that an equation you use is completely balanced, right? Assume that no equations on the exam are balanced until you have checked or otherwise are told, right? The last thing you want to do is do a bunch of math and work for a problem, and then at the end figure out that that equation wasn't balanced, right? Because as we know, we use those coefficients in our dimensional analysis, and so if we don't balance our equation correctly, it's really hard to get the result that we want. Okay, and then what's stoichiometry? Remember, stoichiometry is just basically our math converting from reactants to products or just other chemical species in our equation, right? And we use our coefficients in our balanced formula to do these conversions. In this chapter, we also learn about limiting reactants, right? So limiting reactants will, or these types of problems will occur anytime we're given multiple starting amounts of multiple reactants, right? So if we have a certain amount of A for this equation down here, a certain amount of A and a certain amount of B, right? One of these is going to limit us in how much of product C we can make. In a good kind of real life example to make it make a lot of sense to people is a peanut butter and jelly sandwich, right? If you have 2 pieces of bread and an entire jar of peanut butter and an entire jar of jelly, right, you can still only make 1 sandwich. If you only have 2 pieces of bread, you can't make more than that 1 sandwich. So that bread is limiting. And it doesn't matter that you have the entire jar of peanut butter and the entire jar of jelly, because again, that bread is preventing you from making more sandwiches. Okay, and just note the term excess. If they ever tell you a reactant is in excess, that just means it is not your limiting reactant, and they're not actually going to give you the amount that you start with because it just doesn't matter. Because again, it's in excess, it's not your limiting reactant. And the most common questions you'll face with limiting reactant problems is which reactant is limiting. And so to solve that question, you're going to want to take your starting amounts of all your reactants and just find out how much product can you form. Whichever reactant forms the least amount of product is your limiting reactant. Right? Question 2, how much of a product can be formed, right? So again, this is basically asking not just what reactant is limiting, but then again, when you do the conversions, how much product do you get based on just your limiting reactant. And then lastly, they often will ask how much excess reactant remains. And for a problem like this, you'd actually work backwards, right? So let's say reactant A is limiting. And so to find how much excess reactant you have, you would take the amount of product C that A can make, and then you convert the amount of C that you were able to make from your limiting reactant to how much of B that is equivalent to. And that amount that you solve for of B is how much was used up. And so then to find excess, you take how much you started with minus how much you used up. And again, that's your excess. Empirical and molecular formulas. So you should first note the definitions of these. So your empirical formula is your simplest chemical ratio between the elements in a compound, right? While your molecular formula is going to be your actual chemical formula. So glucose, for example, the molecular or the real formula is C6H12O. The empirical formula, which again is the simplest ratio of the elements, would be CH2O for glucose. Okay, and so for a typical empirical molecular formula question, right, they'll often give you the mass percent of multiple elements. An assumption to make here is that you have 100 grams of compound. By making that assumption, you can drop the percent sign and just write grams. Once you have each atom in terms of grams, right, you're going to convert to how many moles of each of those atoms you have. Once you have moles of each of those atoms, you're going to divide them all by the least number of moles, and this will give you a small ratio between your elements that is in your empirical formula. Now, if you get decimals when you do that division, you might need to multiply by some coefficient to make that ratio whole numbers, because that is a necessary part of your empirical formula. Okay, and then lastly, if they ask for a molecular formula instead of empirical, they would have had to in the question give you the molar mass of your unknown compound. Okay, and so what you do is you take that molar mass of your unknown compound and you divide it by the molar mass of the empirical formula you previously found, right, up above. The quotient of that division is the coefficient you would have to multiply all your subscripts in your empirical formula by to get to your molecular formula. Okay, so let's look at an example of this. Right, so we're given a certain amount of carbon, hydrogen, oxygen, and then we're told the molar mass of our compound is around 222. Okay, and so my first step here, right, I already have grams of carbon, hydrogen, and oxygen, and so my first step I'm going to take is to convert these all to moles, right? So my first step, I get moles of each of these by using their respective molar masses. My second step now is to divide by the least number of moles, right? So my least number of moles was oxygen, 1.67, and so I divide all of them by 1.67, and I get a ratio of 1.5 carbon to 3 hydrogen to 1 oxygen. right? But remember, our empirical formula can't have decimal points in it. And so I kind of multiply all these subscripts just by 2 to get rid of my decimals. Okay, and so my real empirical formula would be C3H6O2. Okay, and this molecule would have a molar mass of 74. Now, I wasn't asked for my empirical formula in this question. I was actually asked for my molecular formula. Okay, and so to find my molecular formula, I would take the total molar mass of the compound, which was 222. Again, that was given in the problem. And I'm going to divide it by the molar mass of my empirical formula. The quotient of this should always be a whole number. And in this case, it's 3. And so that tells me that I have to multiply 3 by all the subscripts in my empirical formula to get to my correct molecular formula. Okay. I think the last topic to cover in this chapter, or one of the last topics, is the combustion analysis. So combustion analysis is actually just a special type of empirical formula question, right? And typically, how we see this problem is that a compound with carbon, hydrogen, and oxygen reacts with diatomic oxygen to make carbon dioxide in water. Okay, and in most of these problems, especially the classic type of problem, they'll give you the mass of your unknown compound and then the mass of carbon dioxide in water at the end. And so an important thing about this problem is that carbon only appears in our unknown compound, and then that will all be converted into carbon into our CO2 at the end, right? And all the hydrogen in our unknown compound is going to be converted to water. Okay, and so knowing the mass of water and carbon dioxide, we can actually work backwards and find the mass of carbon and hydrogen from our unknown compound, right? Once we know those masses, we can take the mass of our unknown compound, which again is given, and subtract the mass of carbon and hydrogen from it, which will give us the mass of oxygen in our unknown compound. Okay, at that point, we will know the mass of carbon, hydrogen, and oxygen in our unknown compound, and from there, we can use our typical empirical formula steps to answer the question, which is typically what's the formula for the unknown compound. Right, and so here's an example of a combustion-like reaction, right? They don't say it's a combustion reaction, but it has the same setup where we have an unknown compound with multiple elements, and on the product side, right, we have these elements with oxygen, and it says these elements are recovered as, right? So that's telling you that all the magnesium, silicon, and hydrogen in our unknown compound became magnesium oxide, water, or silicon oxide on our product side. Okay, and so again, what I'm going to do here is the basic setup for a combustion problem, right? I'm going to take, in this example, the amount of magnesium oxide and work backwards to find how many grams of just magnesium do I have. And what's important about this magnesium is not only is it how much magnesium we have on the product side, but that's how much magnesium we originally had in our unknown compound, right? We do the same for hydrogen and water, and the same for silicon and silicon oxide, right? So these masses that we get at the end, again, are the mass of these elements in the original unknown compound, okay? And I would definitely note that we are not able to do this with oxygen, okay? In pretty much every combustion problem, you will have to do this step to find the mass of oxygen in the unknown compound. Okay, and so we take the total mass of the unknown compound that was given, right? So our unknown compound was about 0.3 grams, and from it, we're going to subtract the mass of magnesium, silicon, and hydrogen, leaving us with just the mass of oxygen in our unknown compound. Okay, once we have the masses of all 4 of these elements, again, we're just going to convert them to moles, then divide them by the least number of moles, and that gives us our ratio for our empirical formula. So chapter 4 opens up with molarity. So remember that molarity is moles of solute divided by liters of solution, right? So every solution has two components. It has the solute, which is typically the solid that is added into the liquid portion, which is typically the solvent, right? Molarity is our most common unit of concentration, and it allows us, or why we use it is allows us to convert between volume and moles. Okay, specifically moles of solute. Okay, we also learned in this chapter about dilutions, right? So dilution is the process of adding water to make a solution less concentrated, right? And so an equation for this is M1V1 equals M2V2, where M represents the molarity or the concentration of your solute, and V equals the volume of that solution, right? So again, this is our dilution equation. And just note that our M1 should always be greater than our M2, and our V2 should always be greater than our V1, right? That is inherent to the process of a dilution, right? We are adding extra water, right? So the volume is going to go up because we're adding that water, and we're adding that water to decrease the concentration or decrease that M value. Okay, and so if you ever see a question, basically, can you dilute to end up with a higher concentration? Just note that your answer would be like, no, that's not possible, or something along those lines. Okay, the last kind of portion of this chapter, which is the big meat of the chapter, is our three types of reactions, right? We have precipitation reactions, which is the first type. So precipitation reactions, on the reactant side, we are going to have ions in the aqueous state, right? Or ionic compounds, I should say, right? You're going to see metal cations paired with metal anions, and again, in the aqueous state. Then when you look at the product side, right, you'll probably see one or maybe two ionic compounds in the aqueous state, but you should also see a cation and anion paired that are in the solid state on the product side, right? That solid product is what we call a precipitate. Okay, and to find what the precipitate is, we use this solubility table, right? So this one in the corner is from your equation sheet. And again, if you don't remember how to use it, remember that the gray areas represent what is insoluble. And remember that things that are insoluble are things that will be in the solid state on the product side, right? So we actually care about what will be insoluble. Okay, so again, the white areas mean everything in that category is soluble. In entire squares that are completely gray, that means that all of those things are insoluble, right? So any group 2 cation, whenever it's with carbonate, is automatically insoluble, right? Every single group 2 cation, if the entire block is shaded like that one is. If it's only one thing shaded, like magnesium hydroxide, that means of all the group 2 cations, only magnesium makes an insoluble solid when paired with hydroxide, right? All the other group 2 cations with hydroxide would be soluble, okay? And then remember our terms net ionic equations and spectator ions. So net ionic equations are, for a precipitation reaction, will only show the ions that participate in the formation of the solid, right? So your reactant side would have a cation and an anion in the aqueous state, and your product should just be your solid. Okay, your spectator ions are any ions that do not participate in the reaction. For a precipitation reaction, that is any ion that does not form the solid, and it would appear in the aqueous state on both sides of your equation. Okay, acid-base reactions. So for this course, again, we focus a lot on acid-base next semester, but in this course, we focus on titrations between strong acids and strong bases. Okay, and remember that our strong acids and bases completely dissociate, right? So if we have 10 molecules of a strong acid and drop it in water, it is going to dissociate into 10 molecules or 10 H plus atoms and 10, if it's HCl, Cl minus ions, right? But if we have a weak acid and there's 10 molecules of that, maybe 2 of the 10 will split up into its ions, but 8 will remain together, right? So that's the difference between strong and weak acids, and it's the same principles that apply to bases as well. Okay, the net ionic equation for a strong acid, strong base titration is always going to be H plus OH minus goes to water, right? And this is the type of titration we focus on in this course. And realize we're going to approach these questions the same way, but they're just going to use several different terms to kind of get you to do this, right? So if you ever see titrate, neutralize, react completely, endpoint, just realize these are interchangeable terms. How you solve this problem is going to be pretty much the same every time. Right, so here's an example. They're asking what volume of 0.4 molar HCl is titrated completely by 60 milliliters of 0.1 calcium hydroxide solution. Okay, and my suggestion to everyone is to always start with the chemical species that you have more information about, right? We have the molarity of our acid solution, and we have the volume and molarity of our basic solution. So our calculations are going to start out with our basic species, right? So I'm going to start with my 60 milliliters of base and convert that to liters. Then I'm going to use my molarity to convert from liters of my basic solution to moles of calcium hydroxide. And something important about these titration problems is we don't actually care about calcium hydroxide or the entire base. We only really care about the hydroxide. So we're going to convert from 1 mole of calcium hydroxide is 2 moles of our hydroxides. And the reason why we care about our hydroxides is that in these calculations, we should always see this conversion factor, that 1 mole of OH minus is 1 mole of H plus. And the reason for this is, again, the titrations we do in this class are strong acid, strong base, and the net ionic equation for strong acid, strong base is H plus OH minus goes to water. So it always is this 1-to-1 ratio, okay? So this allows us to convert from moles of base to moles of acid, right? So we're now in moles of H plus. And so 1 mole of H plus is 1 mole of HCl, and then we can multiply it by 1 over the molarity to find liters of HCl required to make a 0.4 molar solution that underwent this titration. And what we find is it came out to 0.03 liters, which is 30 milliliters. Okay, but there's actually another way we can solve it using this equation. MAVA equals MBVB, okay, where A stands for acid, B stands for base. Okay, but the important thing about this is if you use this equation, which is equally correct as the dimensional analysis, they're doing the same exact thing. The thing I'm just tell students to be wary of with this equation is that notice that the molarity of this has to be the molarity of H plus and the molarity of OH minus. Okay, it wouldn't be the molarity of HCl and calcium hydroxide. It's again of H plus and OH minus. Okay, so the molarity of the base here, because we're talking about hydroxide, should actually be 0.2, not 0.1, which is calcium hydroxide. And if you solve it this way, again, you get 30. So the answer is the same. Lastly, for this chapter, we're just going to touch upon redox reactions. So remember our terminology. Oxidized means that it's going to be an element that lost our electrons, and reduced means that it gained electrons. Okay, and remember that those terms are for specific elements. Okay, now we also have the terms oxidizing agent and reducing agent. Now be careful of the flip-flop here, right? The oxidizing agent will always be in an entire reactant, and it's going to be the reactant that contains the element that is reduced. Okay, and our reducing agent, again, will always be an entire reactant, and it's going to contain the element that is oxidized. Okay. Now moving on, to be able to tell if things are oxidized or reduced, right, we have to be able to assign oxidation numbers, which are kind of like show ownership of electrons. Right, so remember that when we're looking at a compound, the sum of the oxidation numbers of the atoms within that compound must equal the charge of the molecule, right? So if we're dealing with a neutral molecule, when we add up the formal charges, they have to add up to 0. If we're dealing with an ion, when we add up the formal charges, they have to add up to the charge on that ion. Okay, but beyond just compounds, right, we also need ways to figure out the oxidation numbers of individual elements, right? And so remember ions, if it's just an ion on its own, it will have an oxidation number equal to its charge, okay? Also remember fluorine will be -1 always. Oxygen is almost always -2. Unless it's in a peroxide, but I doubt you'll see that on an exam. So almost always oxygen is -2. Hydrogen is almost always +1, but if it's -1, that can happen. But again, on the exam, oxygen's pretty much -2, hydrogen +1. And then also remember that elements in their natural state are 0 in oxidation numbers, right? So carbon solid, solid iron, diatomic hydrogen gas, right? Those oxidation numbers would be 0 in the natural state. Okay, and we'll go through an example that's when problems are released, but how do we balance redox reactions? So remember, we have to split them into our 2 half reactions. Once we have our 2 half reactions, we're going to balance all of our non-hydrogen and non-oxygen atoms, right? So typically that will be just your typically that will be your atom that changes in oxidation number. And you often don't need to balance it. It typically already is, but just check for that. Okay, once that's balanced, you're gonna balance oxygen by adding water molecules to one side of the equation. Then you'll balance hydrogen by adding protons or H+ ions to one side of the equation. And then lastly, you're going to balance electrons by adding, you're going to balance charge by adding electrons to one side of the equation. Okay, and once all those components are balanced, you have a completely balanced half reaction. Okay, and what you want to do when you're looking at your half reactions is make sure that your electrons are on opposite sides, and you want them to be an equal number. Okay, so often you have to multiply your entire balanced half reaction by some coefficient in order for your electrons in your 2 half reactions to be equal and to eventually cancel. Okay, once you've once you've multiplied by those coefficients, you're just going to add all your reactants and products together, cancel out things that are on both sides, right? So just simplify your equation, and at that point your redox reaction would be 100% balanced in acid. Okay, it would be balanced up to this point, this last black bullet point. That's completely balanced in acid. If they ask you to balance it in base, you have to complete these last 2 steps, right? So if you balance it in acid, you'll notice H+ is in your final equation. You can't have that if it's balanced in base. And so what you do is you add equal amounts of hydroxide to both sides of the equation, and you add an equal amount of hydroxide as you have H+. What happens is the H+ reacts with the hydroxide to form water, and then from there you pretty much just cancel out components that are on both sides, which will be that water you just created, and then you'll have your full balanced half reaction, your full balanced redox reaction in base. Moving on to chapter 5. So we have barometers and manometers, right? These are devices where barometers are used to measure the atmospheric pressure, right? And so just remember that on this exam, if they brought up a barometer, they'd probably just tell you your height differential. And just remember that for a barometer, that height differential is equal to your atmospheric pressure, right? And that H is typically given in millimeters, And so remember your units there are millimeters mercury, and that 1 millimeter mercury is equal to 1 torr. Okay, then you also have manometers, right? These measure the pressure of a gas in the device, right? So there's going to be a gas in this little cylindrical bowl here, or this spherical bulb, and the height differential in your column will determine or will tell you the pressure of your gas. Okay, and remember that you can have open-ended or closed-ended manometers. If you have a closed-ended manometer, the pressure of your gas will be equal to the your height differential, right? So you actually read a closed-ended manometer pretty similar to a barometer, somewhat similar. Okay, an open-ended manometer, however, is exposed to atmospheric pressure. Okay, and so these are listed at the bottom of this slide, kind of shows your 3 different situations, right? In your 2 situations, if you have a height differential. And just note that if the mercury level is lower on the side that your gas is on, then the pressure of your gas is the height differential plus your atmospheric pressure. The mercury is higher on the side that your gas is on. The pressure of your gas is atmospheric pressure minus the height differential. Okay, the ideal gas law, right? I'm sure by now you guys are very familiar with PV equals nRT, right? Remember R is that 0.08206 value, right? And the units of that are liters ATM per mole Kelvin, right? Remember to always convert your temperature to Kelvin before plugging into this equation. And on a theoretical level, remember the assumptions we make when we use the ideal gas law, right? Particles of gas occupy space, but in the ideal gas law, we pretend that they don't, right? And so when we are looking at the ideal gas law, we are assuming that there is a greater volume or more volume than the real volume that actually exists. Okay, the ideal gas law also makes another assumption that gases don't really interact with one another, right? They don't exert forces on one another. Okay, and so what this means is in the ideal gas law, we actually have an assumed pressure that is lower than the real pressure that would exist if we did account for the interaction and forces between gas molecules. Okay, we have this type of problem that I call change or before and after problems. And so this is a type of problem where we have initial conditions, and then they'll tell you that maybe 1 or 2 of your variable changes, and they'll ask how a third or second variable changes in relation to some variables that change that you know of, right? So the generic formula for this, a general expression, is written at the bottom of the slide. So P1 V1 over N1 T1 equals P2 V2 over N2 T2, right? This is the general expression that you'll use, and any variable that does not change or you are told nothing about, just cross out of this expression, right? So maybe the number of moles and the temperature don't change, right? So we cross those out and we'd be left with P1 V1 equals P2 V2, okay? And maybe in the situation they say, if your pressure doubled, what happens to your volume? And what you'd find out from the simplified expression is that your volume would have been cut in half, okay? Now we can also get density into our ideal gas law. And this is another thing that I would suggest that you maybe put on your sheet if you are uncomfortable deriving this, right? So our ideal gas law is PV equals nRT. And remember that moles is really our mass divided by our molar mass, right? So I'm gonna plug that in for N, our number of moles. And so we get PV equals mass divided by molar mass times RT. Okay, and our density is mass divided by volume. So if I rearrange this equation, I get that the density is equal to our pressure times our molar mass divided by R times T. Something really important to note about this though, like very, very important to note, is that if you actually look at the units of density here and you cross everything out, your units for density, when you plug it into this equation, has to actually be grams per liter. Okay, this is really important because oftentimes we're given density in grams per milliliter. Okay, and so make sure that whenever you're putting density into this equation, it's again in grams per liter. Okay, a kind of unique or special type of problem we see in this chapter is gas over water questions, right? So typically you will have on your reactant side and also in your setup, right, you're going to have some compound with oxygen in it, right? It's typically some ionic compound and oxygen is in it, right? So the anion portion is probably one of the polyatomics you've studied. Okay, and what happens is a flame will heat up this compound and it's connected to water or a beaker of water. And so as your reactant decomposes, right, oxygen gas is going to flow out and it's going to flow through your beaker of water. And then that oxygen gas is just going to sit above that beaker of water. Now what happens is that you can actually measure the pressure of that oxygen above the water to find how much oxygen you have. But the problem with that pressure reading is that at every given temperature, water has some amount of vapor above it, right? And so when you read the pressure, it's actually it's not just the pressure of oxygen gas, it's oxygen gas plus the pressure of that water vapor as well, right? So it's like contamination. Okay, and so I'll talk about kind of the typical way you have to go about this problem in 1 second, but the key phrase to know it's a gas over water question is they'll typically say water, or I'm sorry, your gas, so oxygen, is collected by the displacement of water, right? If you ever see collected by the displacement of water, it's a gas over water question. Okay, and what's typically given is your total pressure, your vapor pressure of water, your temperature, and a volume. Okay, and so what often you have to do is you have to realize that your total pressure is equal to your vapor pressure of water plus the pressure of oxygen. Okay, and so knowing the vapor pressure of water and the total pressure, you can solve for just the pressure of oxygen. Okay, knowing the pressure of oxygen, the temperature, and the volume, you can then use your ideal gas law to solve for moles of oxygen. Okay, and then from there, they'll often ask you maybe how many grams of starting compound did you have or something like that. Okay, but the big key is knowing how to get to moles of oxygen. So remember, we use the term partial pressures really anytime we have more than one gas in a system. Okay, so the partial pressure is basically just the pressure that that singular gas exerts. Okay, and if they ever say volume percentage, remember that that is analogous to mole fraction, right? So if a gas is 40% of a container by volume, that means that that gas has a mole fraction of 0.4. Okay, and so we have 3 equations that we use when dealing with partial pressures. Our first one is our total pressure is equal to the sum of our partial pressures, right? So total pressure is each partial pressure of gases added together. We also have the equation that the partial pressure of a particular gas is equal to the mole fraction of that compound times the total pressure. And remember that mole fraction is moles of that compound divided by total moles. And then our last equation is really just our ideal gas law, but it's for just an individual gas, right? So the pressure of an individual gas is equal to the moles of that individual gas times RT divided by V. Okay, and T and V aren't denoted with a subscript A here because the temperature and volume is typically the same for all of the gases when there's multiple in a system, while the pressure and the moles are very unique to each individual gas. Okay, we talked about the ideal gas law and the assumptions we make with that, but we also have to be able to understand the real gas law, also known as the van der Waal equation, right? And so we said the ideal gas law assumes that gas doesn't occupy space. And so in the real gas law or van der Waal equation, we acknowledge that gas does occupy a space. And so we use an adjusted volume. Okay, and our adjusted volume is equal to our volume, kind of like our ideal volume, right? Our volume if gas did not occupy space, minus the number of moles n times a constant b, right? They would give you b, or you would solve for b if you had to mathematically do this, right? And so the term nb here represents the volume of space the gas molecules occupy. Okay, and so taking the ideal volume, subtracting that, gets us our adjusted real gas volume. Okay, our pressure, right, we are now going to acknowledge the attraction between gas molecules. And so our adjusted pressure is going to be our ideal pressure plus this term here, which represents the additional collisions between gas molecules, right? So A times N divided by V, and that part is squared. Okay, and so down here is our van der Waal equation, right? We use our adjusted pressure, our adjusted volume, and that's equal to nRT. Okay, the last notes on chapter 5 is just kinetic molecular theory, effusion, and diffusion. Right, so I don't really expect you to have to calculate this first equation. Really, the whole point of this, what the professors want you to kind of get out of this, is that the average kinetic energy of a gas molecule is directly proportional to its temperature, right? So if we raise the temperature, the average kinetic energy of those particles are also going to increase. Okay, and we also have this equation here, our root mean squared velocity, which basically just finds, you know, for any gas particle or gas molecule, you'll have some molecules that are a little bit faster than others, some are a little bit slower. And so root mean squared velocity finds what's the average, what's the most typical velocity these particles have. Okay, and we solve this by doing the square root of 3 times R times our temperature in Kelvin divided by the molar mass. Now this is definitely an equation I'd put on your equation sheet because, or on like a reference sheet for the exam, because I would make big notes that the R in this equation is not our ideal gas law R. It is this other R, 8.3145. Okay, and then the other reason I would write this equation is because when you use this formula, you have to note that your molar mass has to be in kilograms. Right, and the reason for this is that it kind of crosses out with some of the units that make up joules, and when you do this out, your units becomes meters per second, which is the units for velocity. Okay. We have the term diffusion, which is the movement of gases, and it has a net movement of like randomness. Right, they want to move away from each other. They want to reach equilibrium. And so the net diffusion of molecules will again be to less concentrated areas. Okay. Then we also have effusion. So effusion is not just the movement of particles, but it's actually the movement of gas through a specific point, right? It's through a specific hole into a separate chamber in a typical setup. That separate chamber is just called the evacuation chamber. Right, and when we solve effusion, we use Graham's law of effusion. And just note that in this course, we actually calculate relative effusion, right? So we are going to calculate the rate of effusion of one gas in relation to another, right? And so here, it'd be the rate of fusion gas A over rate of fusion gas B. And this is equal to the square root of molar mass of B, right? So notice how B is on the bottom on this side, but on the other side it's on the top, divided by the square root of the molar mass of A. Okay, and so let's say you do this math and it comes out to 3. That means that gas A effuses 3 times faster than gas B. Okay, lastly, we're just going to wrap up pretty quickly with chapter 6 because I just went over this a couple of days ago. So basic definitions, so we have heat capacity and specific heat capacity, which is basically the amount of energy needed to heat things up. And so we only see heat capacity in our bomb calorimeter questions, right? We see specific heat capacity a lot more often. We see specific heat capacity in our Q equals MC delta T equations, right? And we have two things that we focus on in thermochemistry. We have our system, which is typically a chemical reaction, or the part that we actually kind of care about. And then we have our surroundings, which we call everything else. And in this course, our surroundings, especially in calorimeter questions, is going to be water. Okay, and we have two terms that we use to talk about our system, right? And so again, remember, these two terms are only for our system, right? Our system can be endothermic, meaning it absorbs or gains heat energy, or our reaction can be, our system can be exothermic, meaning it loses or gives off heat, right? And if the system gains or loses heat, realize it's doing so in relation to the surroundings, right? So if the system's gaining heat, it's gaining heat from the surroundings. If the system's losing heat, it's losing that heat to the surroundings, right? Which is the big idea behind heat exchange, right? The heat, or Q, gained has to be equal and opposite to the heat lost, right? Equal in magnitude, opposite in direction. We often see this in a classic problem where we have a beaker of water and we drop a hot piece of metal into it. Okay, and so besides the basic relationship of the heat gained and lost is equal in magnitude, opposite in direction, we have this important equation to actually quantify the amount of heat, right? So the amount of heat, Q, is equal to M, which is our mass in grams, times our specific heat capacity, times our change in temperature. Right? And again, remember the change in temperature, this delta means final temperature minus initial. It's always final minus initial. Okay, and again, in thermochemistry, we run a lot of our reactions in calorimeters, right? So we have coffee cup calorimeter, which is a more basic calorimeter, and then we have a bomb calorimeter. So a little bit more complex. We can run more complicated gas and high heat reactions in bomb calorimeters. Right, so the basic premise behind both of these devices is that we will pretty much be running a reaction in these devices, right? And our reaction is our system. Now the water in these calorimeters are going to be our surroundings, right? And the thermometer in our coffee cup and bomb calorimeter is going to measure the temperature of the water. Right, so if our system, the chemical reaction occurring, will either absorb or give off heat energy, and that will cause the water to change in temperature, which we can read via the thermometer. So again, we have the important equation, Q of system equals negative Q of surroundings, again, equal in magnitude, opposite direction, and then from the temperature change of the water, we can use Q equals MC delta T to tell information about our system, which again is typically a chemical reaction occurring. One thing to note about the bomb calorimeter is that our equation for the heat of water is a little different. It has this second term, C bomb times delta T. And so delta T is the change in temperature of the water. C bomb is the heat capacity of the calorimeter. And again, this portion is just needed because of how the bomb calorimeter is actually made and works. Enthalpy. So enthalpy is the difference in heat content between reactants and products at constant pressure, right? So again, I would definitely note that it's difference in heat content, that it's at constant pressure, and definitely note it's a state variables, and that state variables do not depend on the path taken. It just depends on our initial and final conditions. Okay, and if we wanted to calculate enthalpy, the change in enthalpy for a reaction is equal to the sum of the enthalpy of our products minus the sum of the enthalpy of our reactants. And if delta H for a reaction is positive, it's an endothermic reaction. If delta H is negative, it's an exothermic reaction. Okay, thermochemical equations. Just remember that these are balanced chemical equations that have their own delta H value. And you should be very familiar and comfortable with using a balanced chemical equation and its delta H value to undergo stoichiometry, right? So if they give you a delta H for an equation and they say 5 grams of this reactant undergoes the reaction, how much energy evolves. You should be very comfortable being able to use your thermochemical equation to make a conversion factor to help you solve that problem. And if you don't, try to take steps in the next week or so to have that make more sense to you. Okay, Hess's law problems. So we kind of just went over this, and I would recommend, if you want to kind of see examples, last Wednesday in preparation for your multiple choice 3 exam, I went over, I think, 1 or 2 examples of Hess's law in the challenge problem review. And so I would say definitely check on that. I think seeing an example is most beneficial for Hess's law problems. All I want to really say on it right now is that the whole principle of these Hess's law problems is the idea that enthalpy is a state variable, right? So whether it occurs all in one chemical reaction, aka your goal reaction, or 4 different steps, aka your sub-reactions, right? Your delta H should be the same, right? It doesn't matter the path taken, just what you start with and what you end with. Alrighty, and that is all I have. If you're looking for phase change problems, I will be moving, I did teach it in chapter 6, but we'll review it in chapter 10 because it also appears in there. Alrighty, so again, tomorrow night, another video will be posted, that one on chapters 7 through 10. Again, take your time studying. If you have any questions, please write them down as you're studying and bring them to Wednesday night's SI. I'm happy to answer anything. I'll have these slides up, so I'm happy to go to any slides that I ran through that you have questions on. And best of luck studying, everyone.